Time is a prison, a relentless force, trapping us in its linear flow. We exist here and now, believing we have control. Travel back in time before your existence was even a thought. Would you alter reality by just being there? Or is time an eternal beast that cannot be defeated by human? If that's the case, then are we trapped in its cycle forever? Before Albert Einstein introduced his theory of relativity, people thought of time as constant and unchanging, ticking away at the same rate for everyone and everywhere. This idea comes from the laws of physics developed by none other than Sir Isaac Newton. In this concept, time was seen as a universal clock that ticks the same, no matter what happens around it. It was like a river flowing steadily and smoothly, carrying any events forward, from apples falling from a tree to planets orbiting the sun, or even an egg falling and breaking. I mean, by looking at this particular scene, we know exactly what happens first and what happens later. This way of thinking about time was helpful because it made the rules for things like motion and gravity simple and clear. In this classical/Newtonian physics, time was separate from space. It was like the stage on which all events happened but didn't interact with them. This separation meant that everyone, no matter where they were or how fast they were moving, agreed on the order of events. What happened first, second, and so on. Like in the egg example before, we know that in the normal flow of time, an egg should fall first and then break, not the other way around. Essentially, this conceptualization of time was crucial for early scientists and helped make sense of the world in a consistent way. It meant that the laws of physics would be the same yesterday, today, and in the future. And so, the universe seemed predictable and orderly. But then, Albert Einstein stepped in and revolutionized our understanding of the universe. He developed the theory of relativity in the early 20th century. And mind you, this theory relates closely to our description of time in today's topic. Einstein wondered what you'd see if you raced alongside a beam of light and discovered that light's speed is constant, no matter how fast you're moving. This led him to realize that time and space are connected, not fixed and separate like previously thought. In the end, he developed the theory of relativity, which tells us that time can stretch and slow down based on your speed and the surrounding gravity. So, if you see a fast sports car zoom by, remember, time for the driver ticks slightly slower than for someone standing still. But let's not get ahead of ourselves. We'll break this down step by step to understand how that is the case. So let's start with the question, how does the speed of light connect to time? Well, when Einstein discovered that the speed of light stays the same no matter what, it blew his mind about what time could really be. You see, if you were traveling at 90% the speed of light, and you shone a light in the direction you were traveling, it would still travel at the speed of light, not your speed plus the speed of light. For this to be true, time literally could not be the same for you and a motionless observer that is shining his light. The speeds of the lights you two are shining are the same, yet you are moving at different speeds relative to each other. Your time would have to slow down relative to your friend's time for this to occur. And so the whole theory is based on the premise that the speed of light in a vacuum, or c, is always constant. You can never go faster than c, and it will always be the same number. In fact, this has been rigorously tested in lab settings and consistently upheld, like this one that we'll showcase later. In the end, the whole premise would cause a problem if we assumed that time was the same for everyone and everywhere. I know that it doesn't follow our everyday logic, but to visualize how Einstein's theory works in everyday terms, we need to think of time like you're on a train ride through different landscapes. In the old Newton's view, the train would always go at the same speed because the land is flat. But with Einstein's theory, it's like your train speeds up or slows down depending on the hills and valleys it travels over. Steep hills make it slow down, and going downhill makes it speed up. But I have another example that I found intriguing. In this Nat Geo film, we see that Einstein asked his friend to imagine a scenario where he's inside a train moving from point A to point B, with simultaneous lightning strikes observed by a stationary observer. However, according to the person on the train, the strikes are not happening simultaneously.
Now watch the lightning bolts. Were they simultaneous to you? No! Because you were moving towards one and away from the other.
Einstein took this idea even further with his general theory of relativity. He showed that really big things, like planets and stars, don't just sit in space, they actually bend space and time around them. We'll discuss more on this in the latter part of this video. After the concept of time was completely transformed by Albert Einstein, Herman Minkowski, one of Einstein's maths professors, stated that mathematicians should have anticipated the hyperbolic geometry of spacetime. He even went so far as to say that they should be the ones to invent special relativity instead of physicists. 3 years after Einstein published on the electrodynamics of moving bodies, Minkowski delivered a speech called Space and Time to the 80th Assembly of German Natural Scientists and Physicians. He said, "The objects of our perception invariably include places and times in combination. Nobody has ever noticed a place except at a time, or a time except at a place. But I still respect the dogma that both space and time have independent significance. A point of space at a point of time, that is, a system of values x, y, z, t, I will call a world point." On his diagram, Minkowski constructs new x', t' axes that preserve the form of this hyperbola. All of such transformations parametrized by c form a group that he calls GC. In the end, he concluded that the value of c is the one we shall finally be dealing, and it's the velocity of light in empty space. Because the speed of light is exceedingly fast, we often treat it as if it were infinite in our everyday lives. For instance, when referees in an NBA game review the replay video of Curry's three-point shot, they don't consider the time it takes for light to travel to the various cameras. These time intervals are so short, about 30 nanoseconds for a camera 10 meters from one of the crucial events. They are effectively indistinguishable from zero. So in this view, everything that happens in the universe is not just located somewhere in space, but also at a specific time. To fully pinpoint any event, we need 4 details: 3 to tell us where it is in space, and 1 to tell us when it happens. One noticeable exception in real life is the delay in conversations via satellite. I mean, via a Google Meet or Zoom. The signal takes about 1/3 of a second to travel approximately 100,000 kilometers. While this may not make a significant difference in daily life, it highlights an important concept. When I look at you across the coffee shop table, I am not seeing you as you are, but as you were a nanosecond ago. And that, perhaps, is a turning point for some people. By mathematically analyzing the relationships between the speed of light, space, and time, Minkowski developed a new framework. It's the idea that space and time are part of a single 4-dimensional manifold. Where events occur along something he called world lines, he proposed that every object, including you and me, isn't just 3-dimensional, but 4-dimensional, accounting not just for width, breadth, and height, but also for duration, or time. You need to view yourself not only as 6 feet tall, 2 feet wide, and 1 foot thick, but also extending through an 80-year duration. Your world line is like a thread that stretches from your first to your last breath. Minkowski famously stated, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." According to Richard Gotts in his book Time Travel in Einstein's Universe, he states that this does not only challenge our understanding of how the universe works, but it also opens up staggering possibilities for traveling through time. By viewing time as a dimension that can be traveled, we unlock new potential for understanding and exploring the fabric of our universe. But let's be real for a second. While the concept of nonlinear time travel is tantalizing, it's still just a speculative idea. We might not be able to jump through time, but we certainly have the ability to navigate space, moving forward, backward, and even jumping to different points on the globe. I mean, imagine if you could instantly be in another location, not just physically, but digitally. Like, what if you could watch your favorite show in France, even if you're currently halfway across the world? Or perhaps there's a scientific database that's geo-blocked where you are. Well, that's why we partner up with NordVPN for this video. It provides you with access to this spatial teleportation by simply routing your internet connection to a different country. Just like hitting a special button to teleport to wherever you want, NordVPN lets you bypass these digital borders, all with a simple click. What I like most is how secure browsing has become with its Threat Protection Pro. It simply blocks websites that are fake or used for fraud and scams. Everything to make my browsing experience smooth. For anyone who regularly uses the internet, this feature is a must-have. It doesn't even need an active VPN connection. Simply just enable the feature in the app. This is by far the fastest VPN on the planet. So grab the exclusive deal through our link nordvpn.com/beyondideas. You'll get 4 months extra on a 2-year plan. It's risk-free with a 30-day money-back guarantee. In 1971, physicists Joe Haffel and Richard Keating validated Einstein's theory of time dilation in moving objects by taking highly precise atomic clocks on an airplane trip eastward around the globe. During this journey, the plane's speed adds to that of Earth's rotation. When they returned, they found that the clocks were slightly slow by 59 nanoseconds compared to clocks on the ground, a result that precisely matched Einstein's predictions. This phenomenon occurs because of Earth's rotation. The ground is also moving, but not as quickly as the plane. Therefore, clocks on the ground experience less time dilation than those on the plane. Einstein began contemplating the nature of time and its connection to the speed of light as a teenager. He imagined that if he flew away from the town square's large clock at noon, traveling at the speed of light, and looked back at it, the clock would appear to stop, because he would be moving with the light coming from the clock, still showing it at noon. He envisioned looking at the light beam he was traveling alongside. It should appear to him as a stationary wave of electromagnetic energy, since he would not be moving relative to it. However, the established theory of electromagnetism at the time did not allow for such a stationary wave. Einstein concluded that something was amiss. It would take him another 9 years to figure out how to resolve this issue. Not far from 20th century Germany, a physicist named James Clerk Maxwell developed a set of 4 equations governing electromagnetism. Within these equations, he included a constant c, representing the speed that describes the relative strengths of the electric and magnetic forces between charged particles. Maxwell created a clever apparatus to measure this constant. On one side, there were 2 parallel plates, one negatively charged and one positively charged, which attracted each other due to the electric force between them. By balancing the magnetic force between the coils against the electric force between the plates, Maxwell determined the ratio of magnetic to electric forces, and thus calculated the value of C. This value turned out to be approximately 300,000 kilometers per second. Maxwell's work captivated Einstein, but it also troubled him. Einstein imagined what a light beam would look like if he could travel alongside it at the speed of light. According to his thinking, an electromagnetic wave would then appear stationary relative to him, an unmoving wave with peaks and troughs frozen in place, like furrows in a field. However, Maxwell's equations did not permit such a stationary phenomenon in empty space. Throughout the history of science, significant breakthroughs often happen when someone realizes that 2 seemingly different situations are actually the same. Aristotle believed gravity operated on Earth to make objects fall, while different forces governed celestial bodies. Newton realized that the same force causing an apple to fall to Earth also kept the moon in its orbit. He understood that the moon was continually falling toward Earth because its straight-line path in space was constantly being bent into a circle. This insight was not immediately apparent. Something else about light seemed peculiar. Suppose Earth were moving through space at 100,000 kilometers per second. Wouldn't a light beam traveling in the same direction as Earth then pass by at only 200,000 kilometers per second? With the same notion, wouldn't a light beam moving in the opposite direction pass by at 400,000 kilometers per second? So in 1905, Einstein introduced two postulates. First, the laws of physics should appear identical to all observers in uniform motion. Second, the speed of light in a vacuum should be observed as constant by all such observers. At first glance, these postulates seem to defy common sense. How can a light beam travel at the same speed for two observers moving relative to each other? Nevertheless, Einstein went on to prove many theorems based on these postulates. He called this work the theory of special relativity. Special because it applies to observers in uniform motion. Relativity because it highlights that only relative motions matter. Einstein understood that Newton's theory of gravitation complied with the first postulate. According to Newton, the gravitational force between two objects depends on their masses but not on their velocities. Newton had assumed a state of rest, but there was no way to determine, through gravitational experiments, whether the solar system was at rest. According to him, the planets would orbit the sun in the same way whether the solar system was stationary or moving uniformly. Einstein argued that if a unique state of rest can't be measured, then it simply doesn't exist. If gravitation can't establish a unique state of rest, why shouldn't this apply to electromagnetism as well? He concluded that only their relative velocity mattered. Observing the interaction alone, one couldn't determine whether the charge or the magnet was at rest. One of the initial theorems Einstein derived from his two postulates demonstrated that if an astronaut were to pass by you at high speed, you would see his clocks ticking more slowly compared to yours. He envisioned creating a simple clock by allowing a light beam to bounce between two mirrors. The clock ticks each time the light strikes a mirror. Since light travels at 300,000 kilometers per second, or about 1 billion feet per second, it translates to 1 foot in a nanosecond, a billionth of a second. If the mirrors are separated by 3 feet, your light clock will tick every 3 nanoseconds. Now imagine a rocket passing you at 80% of the speed of light. On board is an astronaut with a light clock identical in length to yours. Observing the astronaut's clock as it flies by, you notice the light bouncing back and forth in a zigzag pattern due to the movement of his mirrors from left to right. As the light beam travels from his bottom mirror to the top mirror, you see it moving diagonally upward and to the right, because when the light beam arrives, the top mirror has shifted to the right from its initial position. As the light beam descends, you see it moving diagonally downward and to the right, eventually reaching the bottom mirror again, but at a position further to the right than where it started. The distance you measure for each of these diagonal paths exceeds 3 feet. Since the second postulate states that light must travel at a foot per nanosecond, you observe the time interval between ticks of the astronaut's clock to be longer than 3 nanoseconds. How much more slowly does the astronaut's clock tick? You can determine this. If the astronaut is traveling at 80% of the speed of light relative to you, the diagonal distance covered by the light beam between the mirrors is measured by you to be 5 feet. Since you observe the light traveling at 1 foot per nanosecond, you deduce that 5 nanoseconds pass for each tick of the astronaut's clock. After 15 nanoseconds, you should see 3 ticks on his clock. However, after the same 15 nanoseconds, you observe 5 ticks on your clock. For every 5 ticks on yours, you see his adding 3 ticks, and so you observe his clock ticking more slowly than yours. Now for the truly remarkable part. The astronaut could use his heartbeat as another type of clock. his parallel mirrors, with a light beam bouncing back and forth, and his heart are just two clocks at rest relative to each other, so they should maintain a fixed ratio between their beats. When you observe the astronaut passing by at 80% of the speed of light, you see not only his light clock ticking 3 times for every 5 times your light clock ticks, but his heart also beats more slowly than yours by the same factor. You should see him aging more slowly than you do. When you age 5 years, you would observe that he had aged only 3. Biological clocks and light clocks must slow equally. Otherwise, the astronaut could detect his movement, which would violate the first postulate. In another scenario, if the astronaut passes you at a speed equal to 99.995% of the speed of light, you would see the astronaut's clock ticking at a rate that is 1/100th as fast as yours. After 1,000 years had passed on Earth, people would observe that the astronaut had aged only 10 years. Time travel to the future is made possible by the fact that observers moving relative to each other have different perceptions of time. Such observers can even disagree about which events are simultaneous. In an Einstein universe, universal time does not exist. Time varies for different observers, which in turn opens the possibility for time travel. Imagine a situation where you could travel back in time and meet a younger version of yourself. You might say, "Hi, I'm your future self. I've come back in time to say hello." But what if you traveled back in time and killed your grandfather before he met your grandmother? The problem is clear. If you kill your grandfather, then your mother would never have been born, and neither would you. If you were never born, you could never go back in time, and thus could not kill your grandfather. This dilemma, known as the grandfather paradox, is often considered strong enough to rule out time travel to the past. Although there are physically possible solutions to such time travel paradoxes, physicists are divided on which ones are correct, so let's review all these alternatives. The first concept is the many worlds interpretation. This involves a branch of physics developed in the 20th century, quantum mechanics. A key aspect of this is Heisenberg's uncertainty principle, which states that we cannot determine a particle's position and velocity with absolute precision. Although this quantum fuzziness is usually negligible in the macroscopic world, it is significant on atomic scales. This principle leads, in one interpretation, to the many worlds theory of quantum mechanics, which suggests the existence of different parallel worlds where the particle is detected in various locations. According to this view, the universe contains not just a single world history, but many parallel ones. Experiencing one world history, as we do, is like riding a train down a track from the past to the future. As passengers on the train, we see events pass by like stations along the track. There goes the Roman Empire. There goes World War II. People are landing on the moon. The universe might be like a vast switching yard, with many interwoven railroad tracks. Next to our track might be another on which World War II never occurred. There may have been a moment when Hitler could have been killed, diverting the train onto a track where World War II did not happen. For someone hoping to find a time machine to go back and save a lost loved one, the most comforting thing I can say is that, based on our current understanding, this can only be achieved if the many worlds interpretation of quantum mechanics is true. And if that is true, then there already exists a parallel universe where your loved one is safe. That's because all possible universes exist. Unfortunately, you are just in the wrong one. Another approach to addressing the grandfather paradox is the Novikov self-consistency principle, named after physicist Igor Novikov. This principle proposes that anything a time traveler does in the past was always meant to happen. The universe we perceive is four-dimensional, with world lines weaving through it. If some of these world lines can loop back and intersect the same event twice, then so be it. The time traveler can then interact with an earlier version of himself. The solution must be self-consistent, however. Therefore, you can't change the past, even if you attempt to. If you went back to prevent your grandparents from meeting, something would always intervene. Perhaps you'd end up at the wrong address, or they'd meet elsewhere. It's as if the universe has a predetermined script, and no matter how you try to improvise, the outcome of the play remains unchanged. Finally, there's the block universe theory. This concept views time as a fourth dimension where the past, present, and future all coexist simultaneously. According to this theory, our actions are part of a predetermined timeline, similar to a movie where you can watch any scene at any time, but you can't change the scenes. This means that if you travel back in time, you're not really altering the past. You're merely participating in it, as it has always been scripted. This fixed scenario is very similar to watching films. You can rewind to see earlier parts, but you can't change the story itself. If you're interested in exploring these ideas further, we have a previous video that might catch your interest. Be sure to check it out after finishing this one. Although time travel might sound like it's straight out of a sci-fi movie, but did you know that science fiction often sparks real scientific investigations? Take Carl Sagan, for example. Back in 1985, he was writing a science fiction novel called Contact, which later turned into a popular movie. In the story, Sagan imagined his main character falling into a small black hole on Earth and popping out of another black hole far away in space. To make sure his idea didn't break any actual laws of physics, he checked in with his friend Kip Thorne, a professor at Caltech. Thorne figured out that what Sagan was really describing was a wormhole, not just any black hole. A wormhole is like a tunnel through space-time that connects two different places. Think of the wormhole in an apple. The worm can get from one side of the apple by going straight through its wormhole, then by crawling along the edges. That is how exactly a wormhole works. Thorne found a problem. Wormholes would close too quickly, crushing anything that tried to go through. So he and his team came up with a way to keep the wormhole open using something called exotic matter. This is a special material that's lighter than air, as if nothing is there. This would then allow safe travel through the wormhole. In fact, they even figured out how to tweak the wormhole so that someone could travel back to a time before they entered it, just like a real time machine. This groundbreaking work led Thorne and his team to publish their findings in 1988 in the prestigious journal Physical Review Letters. This idea of taking advantage of wormholes isn't just for science fiction. Perhaps it could actually be used for space travel in the far future. Normally, it takes light about 4 years to travel from Earth to Alpha Centauri. But what if you could zip through a wormhole that Kip Thorne figured out how to keep open? You'd get there faster than light itself. Another problem to be solved is how to attach the wormhole opening where you want them. Perhaps there are microscopic wormholes somewhere already. We're talking super tiny ones, like 10 to the minus 33 centimeters across, which would connect different points of time and space. Some advanced civilization might be able to enlarge one of these microscopic wormholes so a spaceship could pass through it. Speaking of wormholes, we have a fun challenge for you. The person who provides the quickest and most creative solution will win an exclusive chance to participate in our next video. So here's the scenario. It's 2024 and you've always dreamed of seeing a dinosaur in real life. But dinosaurs lived between 252 to 66 million years ago. How could you make that happen? Here are a few hints to help you out. Send your answer to the email below and we'll choose one with the best solution. Anyway, back to the video. The concept of wormhole has a twin possibility in time travel, something called a warp drive. In Star Trek, the crew of the Enterprise used warp drive to alter space so they could travel among the stars at speeds faster than that of light. Theoretical physicist Miguel Alcubierre took this idea seriously and showed how a warp drive could work. In essence, it uses the principles of general relativity. If that could practically be feasible, you could take 4 light-year path from Earth to Alpha Centauri and warp that space so that the distance through the resulting tube would be just 10 feet. So, if time travel with a wormhole involves creating a portal to connect different portions of space-time, Warp drive works by shortening the distance and contracting the space behind you.
You might break causality. If you can't agree in the order of events in time, there's only one way out, is to say that nothing can travel faster than light.
Since all the proposed methods of traveling to the past have their own difficulties, let's consider another idea for communicating with the past. Something called tachyons. American physicist Gerlod Feinberg called such a particle a tachyon after the Greek word tachys, meaning swift. These are hypothetical particles that travel faster than the speed of light. Normal particles like those you and I are made of must move slower than the speed of light. Otherwise, Einstein's postulate that all observers should be able to think of themselves at rest would be violated. And photons always travel at the speed of light through empty space. Since tachyons can beat light beams back and forth, with the help of an astronaut friend, one could use tachyons to send a signal into one's past. This was the basic idea of Gregory Benford, used in his 1980 science fiction novel Timescape. But fitting tachyons into established physics poses challenges. According to special relativity, these particles could theoretically exist, but general relativity complicates things. They would generate gravitational waves similar to a sonic boom from a supersonic plane. Research from the 1970s suggests that as tachyons travel, they emit gravitational radiation, lose energy, and their paths bend into an arch. This results in tachyons and anti-tachyons speeding toward each other, annihilating upon collision. Despite their superluminal speed, tachyons likely can't transmit energy or information over large distances effectively. And so, we face the core issue of how various time travel methods could affect the coherence of our timeline. This brings us to the challenge of addressing these paradoxes within the boundaries of our universe. It was the late Stephen Hawking who proposed the most widely accepted solution to the problem. He said, "The laws of physics do not allow the appearance of closed time-like curves." To put it simply, time paradoxes are not possible. Hawking's famous chronology protection conjecture suggests that the laws of nature are arranged in such a way that time paradoxes simply cannot occur. Whenever you attempt something that could create a paradox, some physical effect will prevent you from achieving that goal. The conjecture argues that the answer lies within this missing knowledge, that one day we might discover a unified theory that explains why time travel paradoxes can never happen. While it may be challenging to accept, the barriers to backward time travel aren't merely technical or energy related. They strike at the very foundations of physics. Yet, the dream of exploring the galaxy remains alive, only at a pace much slower than we might wish, which would then signify that our pursuit of the cosmos isn't driven by personal ambition, but by a commitment to future generations. Perhaps the very impossibility of backward time travel is a hidden gift, urging us to come together for a future that reaches far beyond the limits of our own existence.